In this video, we're going to discuss the other half of thermodynamics and a role that it plays in chemistry. We'll be discussing some new topics known as entropy, free energy, and then the combination of the two of those, which is something we call reaction spontaneity. We'll start with a brief overview of what's going to happen in this video. We'll begin our discussion with a review of some of the enthalpy topics we've talked about so far this year. However, we're going to focus on a new area of this world of enthalpy by discussing the idea of favorability, whether or not having certain enthalpies is favorable for a chemical reaction to be able to happen or not. Once we finish our review of enthalpy, we'll discuss the new topic in this video, the other half of the thermodynamic world, which is entropy. We'll define what entropy is, being a very difficult concept to wrap your head around. We'll follow that up with some examples to help you kind of think about what it means to have a positive or negative entropy. Last but not least, just like the conversation in enthalpy, we'll finish up with a discussion of how this adds to the favorability of a chemical reaction happening or not happening. Those two ideas, enthalpy and entropy, will lastly be combined into something known as Gibbs free energy, a simple equation that is used to calculate and figure out whether a chemical reaction will occur when you put the reactants together in a flask or whether the reaction will not occur. This is something known as reaction spontaneity and has a lot to do with this picture over here to the right of icicles. We all know that when these icicles form during the winter time, that at some point in time they'll eventually melt off of the side of our homes. This happens because eventually the ambient temperature around the icicles exceeds the melting point of water, 0 degrees Celsius, and the melting process begins. In this video, we'll discuss about the physics happening behind the scene that makes that temperature 0 degrees so special for water that causes melting to happen after 0 degrees, but not before. As I said, we'll begin our discussion with a review of some of the enthalpy topics we've covered so far in this unit. The symbol we use for enthalpy is going to be the symbol delta H. Again, nothing new there. As you recall, enthalpy is all about this concept of heat energy, and that's either generated as a product, making the reaction exothermic, or that heat energy is used as a reactant, making that reaction or that delta H value endothermic. Again, a recap of stuff we've already seen. The heat energy that is used or generated in these chemical reactions comes from the breaking and forming of chemical bonds. Ultimately, the net difference in the energy released and formed by breaking and forming these chemical bonds is what results in our delta H of reaction. And this has a lot to do with the idea of conservation of energy. If we have excess energy left over from one part of the reaction that doesn't get used in the other, that excess energy has to go somewhere. And in this case, it comes out of the reaction in the form of heat energy. All of this information ultimately combines into this idea of whether or not a reaction is going to be spontaneous or not. We've already identified earlier in the unit that when delta H values are negative, or when the reaction is exothermic, this reaction is more likely to happen. And the reasoning behind that is that the reaction already has enough energy to run by itself. When the reaction is endothermic, there has to be an outside source of energy around. If that outside source is not available, the reaction doesn't necessarily happen anymore. We can therefore summarize this information to say that if our delta H value is going to be a negative value, we would say that this is something that is favorable for our reaction to be spontaneous, whether or not a reaction can happen by itself. Likewise, if our delta H for our reaction is a positive value, we would say that is unfavorable. It is unlikely that this chemical reaction can happen on its own. It's unlikely that this reaction can be spontaneous. Now again, we're using the words favorable and unfavorable, and that's going to be something we'll address a little bit later on. There's more to this puzzle than just the enthalpy involved. So let's see enthalpy at play a little bit. Here's some of the reactions we performed together in class. This CH4 is one of the primary ingredients that we use in natural gas. We burn some natural gas in class in the form of bubbles. It reacts with 2 oxygen molecules to create carbon dioxide and 2 water molecules. And the delta H of this reaction is very negative, a relatively large negative value. As a result of that, we would say that large negative value makes for a very favorable enthalpy, and it's going to make this reaction likely to be spontaneous. And as we saw in class, this reaction was spontaneous. Once I lit the natural gas bubbles on fire, they burned all by themselves until eventually all the natural gas was done. I didn't have to keep putting in more energy to keep the reaction going. So this is a favorable situation enthalpy-wise, and the reaction ended up being spontaneous. Here's another reaction that's hopefully a little bit familiar. We take carbon dioxide and water molecules and add them together, and ultimately this forms this substance here, which is glucose. This is the reaction that happens during photosynthesis in plants. The delta H of this reaction is a very, very large positive value, and as a result, we would think of this as being something that makes this reaction unfavorable. It is unlikely that this reaction will happen by itself, and as a result, we expect this reaction to be non-spontaneous. It requires the continual input of energy to run, and that is indeed the case. If you need evidence of this, our atmosphere is filled with carbon dioxide and water, and we don't expect sugar, glucose, to come raining down in the atmosphere at any point in time. This reaction only happens with a significant input of outside energy, and if you think about photosynthesis, that outside energy comes in the form of our sun, and without the sun present, photosynthesis would stop because we wouldn't be able to provide this quantity of energy without such an abundant source. So far, we've been able to define two reactions, one having a favorable enthalpy, creating something spontaneous, and one having an unfavorable enthalpy, creating something that's non-spontaneous. And generally speaking, that's going to be the rule. Negative delta H's make spontaneous reactions, positive delta H's make non-spontaneous ones. As with so many things, however, there's always exceptions. Here's the second reaction we were able to perform in class. We took barium hydroxide, we reacted it with 2 moles of ammonium nitrate to make barium hydroxide, ammonia, and water. The delta H of this reaction is a positive value, and as you might suspect, this is unfavorable for our enthalpy. The problem with this particular reaction, though, is that despite having an unfavorable enthalpy, this reaction is still spontaneous. When I mixed these two chemicals in the beaker in class, they still reacted together. The flask got very, very cold. And if you do enough of it, like I have in this picture, you can actually get the flask to freeze to the board. This reaction happened without me driving it forwards like I would have had to done in the photosynthesis reaction. So this is an exception to what we've identified up here. The next thing we need to start doing is explaining why this reaction is able to be spontaneous despite not having a favorable enthalpy. So if you can't explain the entire process using just enthalpy, that must mean there's another force at play, and enter this new concept of entropy. Just like enthalpy has a symbol delta H, entropy has a symbol of delta S. And basically what it is, it's another form of energy that a reaction can use in order to generate chemical products. What I have next is a more technical definition of what entropy is all about, and unfortunately, like most technical definitions, it's a little difficult to work with. It's a thermodynamic quantity. It's an amount of energy that represents the unavailability of a system's thermal energy for conversion into work. So basically, the question is how much of the energy available in my system is capable of doing work? Entropy is a measurement of the opposite of that. How much of it is unavailable to do work? Entropy is often interpreted as a degree of disorder or randomness in a system. This is actually not a great way of defining entropy. Disorder and randomness is kind of the result of systems that have high entropy, but not really what drives the force of entropy itself. And hopefully we'll be able to make that distinction a little further on down the road. What I can say at this point in time is that it's something driven by statistics, probabilities, the likelihood that one outcome is going to occur versus another set of outcomes. And again, we'll hopefully clear some of that up in this the role that statistics plays a little on down the road. Before we start with those examples, however, I do have one thing I want to throw out there. There are laws of thermodynamics, just like you have physical laws provided by Newton. And the second law of thermodynamics deals with entropy. And basically what the second law of thermodynamics does for us is it tells us that the total entropy of an isolated system can never decrease over time. What this really means for us is that when we start talking about changes in enthalpy, the universe is going to favor changes in enthalpy that are positive, things that increase entropy over time. Just like we said with delta H, when we have values of delta S that are positive, we'll say that these are favorable towards a chemical reaction being able to produce or proceed spontaneously. When we have delta S values that are negative, we'll say that that is unfavorable. And just like we showed with the delta H values, seeing these delta S values can give us hints as to whether or not our reaction will or will not occur. So let's see if we can try and wrap our heads a little better around this concept of entropy. What I have here on the screen is a picture of a pile of bricks. And as silly as it might seem, I do hope that you would take time to either draw or find an image of a picture of a pile of bricks that you can include in your notes. I think it's going to be pretty central to the discussion we have for this. First of all, we would say that this pile of bricks, let's label it as what it is here. We have a pile of bricks. And we'll start with our simplest definition of entropy, the idea of disorder or randomness. And we could say that this pile of bricks has a very high degree of disorder, which means we can say that this pile of bricks has a very high entropy. Now, the real reason we can say this pile of bricks has a very, very high entropy is because of the number of ways that we can create this pile of bricks. You can imagine if I took a dump truck, dumped all the bricks out of the back of the dump truck, there is a very high probability that we would get a pile of bricks very similar to the one that we see in front of us. Likewise, there's a high probability that we would get a pile of bricks similar to this one or a pile of bricks similar to this one. All these piles are different from one another, but at the end of the day, they're all the same thing, a pile of bricks. And if we dumped bricks out of the back of a dump truck millions and millions of times, almost every single time, we would get one of these possible outcomes. So the end result is we can say that this has a very high entropy because this is a very likely outcome for many bricks. When we use those many bricks, we would expect them ultimately, when dumped out randomly, to form a pile like this. Now, conversely, we could look at a much different situation. Here, we have a brick wall. This brick wall represents a very low degree of randomness, a very low degree of disorder, and as a result, we would say that this brick wall has a very low entropy. You can imagine again with our dump truck. If we dumped bricks out of the back of the dump truck, it is extremely unlikely that they would form themselves into this very specific pile here, which creates a brick wall. So this is a very unlikely outcome for our pile of bricks. And you can imagine there is certainly a possibility that when you dump those bricks out of the back of the truck, they'll land just right to create a wall just like this one. But we might try that every single day for our entire lives and probably still never see it occur. It is such an unlikely outcome, we would more likely expect this situation over here. Now let's start tying this then back into the idea of delta S. If I try to take my pile of bricks and turn it into a brick wall, we would go from a very high entropy system to a very low entropy system, making our change in entropy something that is negative. We would not expect this to happen naturally because our second law of thermodynamics says that the universe prefers delta S's that are positive. And I think we can all agree that none of us have ever seen a pile of bricks self-assemble itself ultimately into a brick wall. In fact, if you want to make this happen, you have to put energy into that process, right? You have to invest muscle energy, you have to eat food, you have to spend time planning this. There's lots of work that goes into turning a pile of bricks into a brick wall. Conversely, if we were to see the opposite reaction happen, going from a low entropy system to a high entropy system, this would create a delta S that would be a positive value. This is something we would expect to see happen. If, say, for example, my brick wall was sitting out in front of my house and a tree fell down and hit that brick wall, we would expect the tree to take the brick wall and convert it from the wall into the pile of bricks. No work or effort on my part to have that happen. The universe naturally drives things towards low entropy systems, ultimately to high entropy systems. And in fact, we could say that this process would actually have some energy coming out. Not necessarily with the brick wall, but we will see this happening when we talk about this at the atomic level in chemical reactions. So to summarize, entropy is all about how highly ordered your system is. How many likely outcomes are there for your system in one state versus the other? And then the natural progression will always be to move from the highly ordered, the less likely outcome, to the highly disordered or the more likely outcome. And this is not because of a force driving this, but again, it boils down to the statistics. If I do anything to upset this wall, it's likely to turn eventually into a pile of bricks. But upsetting the pile of bricks is very unlikely to turn itself into a brick wall. Let's take a look at this effect in the form of a chemical reaction. We again have our barium hydroxide reaction from before, that we had an unfavorable enthalpy before, and we were trying to explain how this reaction could possibly be spontaneous despite the fact that it doesn't have that necessary energy. Well, if we include information about the delta S, we can see that this reaction has a very favorable entropy. There is a big increase in disorder in this system, and one of the reasons being is we create a lot of smaller products from just a couple of larger chemicals. We go from an organized system where all the molecules are bound together in a very specific way to a slightly less organized system where there's fewer individual particles that can behave independently. That creates a very positive value for delta S. It's ultimately the combination of the delta H and the delta S that determine whether a reaction will or will not be spontaneous. So we have to take that enthalpy and the entropy combined in order to actually make this prediction. And this brings us to our final topic covered in this video, the idea of Gibbs free energy. What free energy is basically the net available energy available to drive a chemical reaction forwards. And as we just talked about, it's the combination of the enthalpy available in a chemical reaction and the entropy in a chemical reaction. The symbol we use for Gibbs free energy is delta G, and it can be represented with an equation. Delta G is equal to delta H minus T delta S. If you recall, our delta H is our enthalpy, our delta S is our entropy, and our T is our temperature in the units of Kelvin. And as we mentioned earlier in the video, we talked about negative values of delta H being favorable to spontaneous reactions and positive values of delta S being favorable to spontaneous reactions. If we take a negative number minus a positive number, what that tells us is that when values of delta G are negative, we can therefore say our reaction must be spontaneous. The enthalpy is saying it's spontaneous, the entropy is saying it's spontaneous. There's no possible way that this reaction can be non-spontaneous. A negative number minus a positive number generates a negative answer. Therefore, negative delta G's make for spontaneous reactions. Likewise, when delta G is a positive value, we would expect our reaction to be non-spontaneous. Let's see this Gibbs free energy equation in action a little bit. We're again going to take a look at our barium hydroxide reaction. We have our values for delta H and our values for delta S. Our equation, delta G, can then take these numbers and actually plug them in. We plug in the positive 135 for delta H, minus 298. This is our room temperature. So this is the temperature of our classroom when we performed the reaction. I took our delta S and converted it from joules into kilojoules to get 0.535. And all this comes out to give us a negative value for our value of delta G, again giving us information that this reaction is going to be spontaneous, which is what we observed in class. You can see then that this reaction, however, is not always going to be spontaneous. If we change the temperature up or down, that's going to change how big this delta S impacts the outcome of the experiment, and we could possibly get a scenario where this reaction would be non-spontaneous. So let's see if we can summarize this. Over on the left side of the screen here, we have all of our outcomes for enthalpy and entropy, unfavorable versus favorable in both cases, although we do point out the fact that the entropy is something that is temperature dependent. And last but not least, we identified positive and negative values for delta G as ultimately deciding whether the reaction would be non-spontaneous or spontaneous. We can take this information and the equation and summarize it into 4 possible outcomes. For example, if delta S is greater than 0, which is a positive delta S, and delta H is less than 0, which is a negative delta H, we said a positive delta S was favorable and negative delta H was favorable. Because everything's favorable, we would expect this reaction to be spontaneous at all possible temperatures. Likewise, if we look at the opposite outcome, a negative delta S and a positive delta H, those are the two unfavorable outcomes for enthalpy and entropy, and that makes for a reaction that is always non-spontaneous. The other two outcomes here shown in yellow are when delta H and delta S disagree with one another. One's favorable and one's not, and these will be situations that are what we would call temperature-dependent outcomes. This outcome is spontaneous at low temperatures, whereas this outcome is spontaneous at high temperatures. Please make sure you take a moment to copy this table down into your notebook. We will use it next class as a tool to predict whether a whole bunch of reactions are going to be spontaneous or non-spontaneous. And that brings us to the end of our video. At this point in time, you should be able to define the concept of enthalpy versus entropy. You should be able to describe enthalpy values and entropy values as either being favorable or unfavorable towards driving a chemical reaction. And then ultimately, you should be able to predict reaction spontaneity by combining that information into the Gibbs-free energy equation. You can do that either using the table or by actually doing some of the very simple mathematics. Back at the beginning of the video, we talked about the fact that this concept would be something we could use to explain why icicles melt once you reach a certain temperature. And again, think back to your Gibbs-free energy equation. Delta G is equal to delta H minus T delta S. In this scenario, the enthalpy of ice melting is a positive process. It takes energy to get the ice to go from the solid state to the liquid state. We learned that a couple chapters ago. The entropy, however, of this scenario is also positive, and if you reference back to your chart, this is one of those situations that makes this scenario temperature dependent. As the temperature gets higher and higher, it makes the impact of the entropy value get larger and larger, and ultimately this value gets large enough so this positive number here, subtracted from this positive number, ultimately creates a scenario where our delta G ends up being a negative value. So there's a minimum possible temperature where the melting of ice process must become spontaneous.